Hello, this is Ryan Woodward. This is a recording and a little walkthrough of a parallel adder circuit that I wrote. And this leverages a full adder circuit. And we can see real quickly that this is the full adder circuit. I won't do a demo of this individually because it's a basic full adder. You can find them everywhere on the internet. But it's as simple as it is. It adds two bits together, X and Y, and if those are high, we'll have a carry out. And the carry in is a part of that for the parallel adder specifically. And we can see that sum is X and exclusive OR Y, exclusive OR C in, and then we have C out being X and Y or C in, or C in and Y. And that will make sense a lot later. If we were to look at the truth table, we could see that basically if we were to add 1 and 1, we'll get 1 and 0 will get 1, 0 and 1 will get 1, 0 and 0 will be 0, and 1 and 1 will also be 0 with 1 at the carryout. And I also wanted to note that I did this in Verilog as well. Because I had it written in VHDL, which is honestly my preferred HDL, it was very easy just to add this in Verilog and make it happen, do it that way. So for a parallel adder, I use a structural, it says behavior, but this is actually a structural model where we actually declare a parallel adder, or excuse me, a full adder component, and these ports here are identical to those as I showed in the full adder there. We declare 4 full adders, full adder 0 to 3, and we port map those to these ports above in the actual entity declaration of the parallel adder. We have A 0 to 3, that's a 4-bit value, then B 0 to 3, another 4-bit value. Our sum will be an output for a 4-bit value, and then the carry out for those instances where we have, for instance, it'll be anything greater than 15 overall. So if we were to add 8 and 8, those two, maybe it would be A3 and B3, that would give us a value of 16. The LEDs will be low, but the carry out LED will be high. And it's really that simple. It's not much to go. I do want to point that in this circuit, though, we do have some intermediate signals, and for each part that would normally be a carry in, we have C1, C2, C3, C4 being corresponding to each of the following circuits there. And C out receives the final output. And note again, I did this in Verilog as well. And once I had it compiled and running in VHDL, it wasn't very hard to actually get it decoded in Verilog. But I'll do a demo of this. All right, and this is our parallel adder. So unlike a 4-bit adder subtractor, which you might have seen in another video, this cannot subtract. This can only add our two values, but it actually does have a carry in. And we will be able to see similarly how in that 4-bit adder subtractor that if we were to add greater than 16, that it will have a carry out. So we have 8, this is B3 and A3. Those being high, because they both have a value of 8, will actually pass 16 to the out, and we'll have that low. We could accomplish the same thing if we were to add all of A3, this would be A being the value of 15, plus B0 to be 1, we'll get 16, and then I'll send that out. But just a quick demo that it's actually adding everything. If we were to add, this would be switch 3, A2, would be a value of 4, and if we were to add 1, we'd get 5, 2, we'd get 6, and add another 4, we'd get 8. All right, and that's the 4-bit parallel adder.